Hello, this is Logan Mayer Walford, and welcome to my explanation of Problem 2 for the paper homework for Chapter 11. So, first off, as we can see the problem, we have a uranium atom that is going through radiation decay. It emits an alpha particle, which we know both the mass and the velocity of. I have highlighted both of those in green. And we now understand that we have a different atom, thorium, and we have its mass. But we are asked to find the speed and the direction of this thorium atom. Well, technically it's a nucleus, but this is physics, not chemistry. So, first off, how do we set up this problem? Well, as you see, I have an initial and an end, meaning that I have understood that this problem happens in two stages of time. We have before the decay and after the decay. After the decay is going to be the important aspect for us. Well, why is that? Well, this is a conservation of momentum problem. Or at least that's the easiest way to do this. And the reason for that is momentum states that the momentum of the initial point in time, the whole atom, is equal to the momentum of the final time, or the end, when we have two particles. That means, if we understand what momentum is, momentum being velocity times mass, we can understand that the mass of 1 times the velocity of 1 is equal to the mass of 2 plus the velocity of 2. Sorry, that should be a times, not a plus. This is what you get for doing all your physics homework at once. Plus the mass 3, velocity 3. That's a times again. Don't want to make the same mistake twice. So, if we just look up here, we see that these are some really hard to write out numbers, and I don't want to try to write out 17 digits worth of numbers. So instead, we'll just assign each of these a value m1, m3, m2, and velocity 3, respectively. Why don't we have a velocity 1, you might be saying? Well, that's because we're saying that this particle is at rest. We're assuming that velocity 1 is equal to 0. I've put that right up here. And I'll put all of our fundamental equations right over here. Just so we understand what that is. I'll label this fundamental equations. So, if we know that any number times 0 is 0, we know that these two numbers, when added together, have to be 0. Well, that's pretty nice, because that means that mass 2 times the velocity of 2 is equal to negative mass 3, velocity 3. And if we're solving for velocity 2, well, it's negative mass 3, velocity 3 over mass 2. Scroll down just a little bit. Okay, well now we have our equation. And if we plug in all relative and important values, the values highlighted up here, we see that we get negative 24295.1785, or in scientific notation, as it was given to us, 2.429521. You see, it's not a second period. One period. It's a decimal. What was that? 4. Sure, 2 stands out. 21785 times 10 to the 1, 2, 3, 4, 5. 10 to the 5th meters per second. That is stupid fast, but makes sense. And that is our speed, but not our direction. For the direction, we have to remember momentum means 0. And so if I have a particle speeding off to the right, and if the entire system has to act like nothing is really happening to it momentum-wise, they have to cancel, meaning I have to have an equal and opposite momentum the other way. So it has to go to the left. To the left. And that is our final answer. Thank you so much for joining me. See you again soon.